I want to discuss about the Reynolds number and its derivation. Okay, so the question is where are the Reynolds number originated? Okay, and also its derivation and implications. Okay, so first, in fluid mechanics, we can define, apply for Newton's law, and that you can see. So, like basically, all the external forces applies for mass times acceleration. Okay, so or this is mass times dt, the velocity. So external force is composed of pressure gradient, and also viscous forces, and etc. So now that can be translated into fluid dynamics. So mass is becoming a density dv. Let's use u vector dt, and then pressure gradient can be defined as negative this, because of pressure gradient. You know that fluid flow is direction of high to low pressure, so that is minus gradient p, and viscous force is a mu. This is like that, so plus viscosity mu, and this plus etc. So this has a unit. So this is a total derivative, and this d dt in fluid mechanics, d dt, it can be partial derivative plus d u. You can write it down in this way. So let me write this one again. So this is called Navier Stokes equation, which is written as Navier Stokes equation, which is a Newtonian law converted into viscous fluid. So that is, let's normalize. First, write it down this equation again. Sorry. Write down this equation again. One becomes low u round x plus v round u round y. So you have velocity vector can be x and y decomposed into x and y. So this is a assumption is now I think we can say the assumption two-dimensional and incompressible. So it's not like air, it's like fluid. Usually fluids such as blood is incompressible, and also steady state. So a simpler form, and then this becomes pressure gradient. Just assume one-dimensional case pressure gradient, so only round xp plus so 1d direction case only. So let's simplify. Then mu only x direction, so round square u plus etc. So this is 1 prime. Then let's normalize the equation number 1 prime. Normalize the equation 1 prime by, so to normalize, we need to use some characteristic dimension or physical quantity. So for example, length of a length such as L would be a characteristic length. If it's duct, it can be a diameter. If it's on top of airfoil, then the length could be the distance or length of the pipe. So L, so we normalize, we can define as X star, so it can be defined as X over L. Velocity, so we can normalize with U, let's say capital U, so that U could be the original speed of the flow. So that can be U, little u star can be defined as a U over this, or V star for 2-dimensional case, V over U. Okay. And then what about pressure? Yeah, such as atmospheric pressure. So we can define normalized pressure by P P star. Okay, so normalized big P as, let's say, like this P, that can be also defined as from Bernoulli's equation, pressure is the same unit of rho times this velocity square. Okay, so so we can define normalized pressure as pressure divided by this capital P. So then 1 prime becomes, so you can rearrange and simplify and this 1 prime, which is this one. Okay. This will turn into, so left-hand side, is you can push the load downwards so that U prime round U prime, U star round X star plus V star round U star over round Y star equals the pressure gradient, because rho can be round P star over round X star plus, in fact, 1 over all the parameters get into here, okay, and then while the other will look like round star round X star round X star square plus etc. Okay, that you can define as 2. And you know what? All the parameters here, we just define, let's say this is Reynolds number. Then what you will find where the Reynolds, you define Reynolds will be rho times velocity times characteristic length divided by mu. So this we define as, called as a Reynolds number. Then one can interpret this as Reynolds number. Let's say, let's to understand and make some sense of this new definition of Reynolds number, which is coming from there. In fact, it is rho V over L over mu, and let's make it the dimension of, let's say, pressure, which is force divided by area. So that becomes U times rho U square divided by mu times velocity over L. And that you can be familiar with. This is in fact inertia. Inertia force and divided by viscous force. Okay, because the reason why this makes sense is, you know, that CF, I'll call, so 1/2 log v squared. This is inertia or kinetic energy, okay, versus mu round u round y. So this is where viscous force is defined. So this is actually shear stress. Okay, so from here, you can actually make sense that Reynolds number, the implication is the ratio between inertia and viscous forces. And so this interpretation, what it means is, now you can see that if that normalized Navier Stokes equation will hold for the same Reynolds number. So what can we use it for is, let's say when we design an airplane, which is a big Boeing 747, and that fluid mechanics, what happens, the flow through the body and the airfoil will be the same when you make a smaller system to experiment, when you match this Reynolds number the same. So you can actually do the experiment much easier, simpler way to predict what can happen by using this normalized approach, only by adjusting this Reynolds number as the same. So keep the Reynolds number the same, then the flow phenomena will be the same. So that's the point. Thank you for your attention.